I started off the year by going back to Malibu. The air was clear as can be and visibility the best I've seen it. We'll be watching the world in the visible spectrum, then switch to infrared, and you'll behold a world like never before. So I walked out at the Point Dumais Natural Preserve, very nice observational location, and most of my filming was from about halfway up. It was a bit windy, so I stayed on the left side of that hill there. And anyway, here's a clip. This is what you saw in the visible spectrum. You could barely see Mount Baldy there, and that's Point Palos Verde right there, and Catalina, kind of like through haze, atmospheric haze. The altitude was about 150 feet, right about here, and up top is about 200 feet. I'll use that later to do an analysis of what we're seeing. Now let's zoom in a little bit here to see, this is just a photo. See, we can barely see Mount Baldy. It's about 70 miles away. But notice we don't see anything else out there. But in infrared, it will show up clearly. Have a look at this miraculous imagery.
Look at that, San Jacinto from Point Dumais. Just unbelievable. Santa Monica right there. There's LA.
Now let's have a look at some high resolution infrared photos. Look at that, folks, so much resolution, 24 megapixels. This was taken with the Sony Alpha 6000 converted to 830 nanometer infrared. Look at that, just incredible. Infrared is an amazing technology, folks, but even more amazing is what it reveals. Behold the flat earth, folks. This image is so powerful. Just have a look at this, folks. That mountain is over 123 miles away. If we were living on a globe, that mountain should not be visible. It should have dropped behind the curvature of the earth. But the earth appears astonishingly flat, folks. It's a very mysterious, strange phenomena. We'll do an analysis shortly because there's some very interesting things revealed in this image. Let's have a closer look. Due to the clarity and high resolution of this image, we can identify a few features. But notice something very interesting. Notice the difference between feature A and B. It's a delta of about 300 feet. And between C and D is a delta of 600. But wait a second, those distances are about the same in angle. But then look at the bottom, features E and F, it's about 2,800. Isn't that incredible? There is a non-linear compression that is occurring here, folks. So I built a scale in milliradians based on the spacing between A and B because it is more accurate. Basically, the steeper the angle, the more accurate it is due to atmospheric refraction. And that mountain should actually come up to about 17 milliradians. So it's slightly compressed. It comes up about 14, just shy of 14. Very interesting phenomena here, folks. Compression. So we actually see the entire mountain, but it is compressed, which is very strange, but really, when we think about it, not unusual. When we see the moon rising, for example, sometimes it begins out kind of flattened out. It's what the atmosphere seems to be doing, kind of flattening things at low, grazing angles. Now I've studied these features in Google Earth to identify them, and here's a short clip and some pictures so you can see what it takes to kind of identify these features. Here's a Google Earth snapshot with the labels that I had on the infrared picture. It takes a lot of work to really identify these features. As you'll see shortly, I've used Google Earth and panned around, zoomed and tilted until I convince myself of what I'm seeing. Have a look. See, by moving it back and forth, we can tell what we're really seeing. And one has to really study everything closely. Notice how things are not in proportion to how they were in the image. It's because of that compression that has occurred. But here's that face, and we can see that that notch. I'll point to it in a second. Right there, you see that peak and that notch? Those are key identifying features, and it casts some shadows. So yeah, the lighting is obviously different, so one has to really think about what it is they're seeing in the picture, and also be mindful that we're seeing this from far away and the perspective is different than being close up in Google Earth. So if the Earth were spherical, that peak should be visible where I drew the bottom yellow line. I mean, look at that drastic difference. In the lower right, there is a graphic kind of illustrating the geometry for a curved Earth. Notice the dotted blue line drawn tangent to the mean sea level, and then the red line drawn above it tangent to the foreground obstructions. And basically, based on the calculations on the left, lower left, I conclude that about 1,500 feet should barely be visible above the foreground obstructions, the buildings and whatnot. So very drastic difference here, folks. Yeah. Just to go through the calculations here real quick. The mountain height about 10,800. The observational height is at 150 feet, which puts the horizon at about 15 miles. And that's good because the distance to the shore is about 19 miles. Now, the curvature should be hiding about 7,800 feet at mean sea level. And the land obstructions assumed about 250 feet at 20 miles. after using Google Earth and just just looking around along the path to see what kind of height there are. So anyway, that translates to higher obstruction distances at 123 miles out. So anyway, I calculate about 9,300 feet of obstruction. And so that leaves about 1,500 feet that should still be visible. But at those distances, that would be like a sliver where that yellow line is. Basically, you wouldn't be able to tell there's a mountain there. But there it is, folks. There's the mountain just standing up proud. Isn't that crazy, folks? We've been told all our lives that we live on a ball, yet it doesn't seem to check out, which is very weird. The atmosphere obviously occupies the intervening space between us and the mountain, so it's imperative that we understand how light behaves as it propagates through the atmosphere. I'm going to share with you folks some insight I've gained in the past year that convinced me that we do not understand refraction properly, and that indeed the earth is flat. Have a look at this incredible evidence. Using an app, a theodolite app that measures angles, I noticed that the horizon over water is not where it's supposed to be. Here I'm just standing on the beach in Key West, Florida, and it's not where it's supposed to be. And so when I measure it, it is down at about 1.2 degrees, which really got me thinking. Since the horizon appears much lower, that means light is curving upwards, bringing the horizon down. And this actually explains a lot of things, why ships seem to disappear over a curve, perceived curve. But it's actually, folks, a mirage, a long distance mirage, as this illustration shows. Since light is curving upwards, it will intercept the surface, and anything below that will not be visible. So looking at that cruise ship, below that blue line you shouldn't be seeing it, but above you will see it. Now I've tabulated in the lower right a few elevation angles to the horizon given the observer height. And so at an angle of about 1.2, we're probably somewhere upwards of 1,000, maybe 5,000 feet. But we were standing on the beach. Isn't that incredible? It's really light refraction upwards that's doing this. I've been speculating that this refraction is caused by the evaporative boundary layer, but I had no proof until this past summer. I was in San Diego, in La Jolla, and when I measured the horizon, I realized there is a tilt to the right, which really puzzled me. Notice that the surface, the horizon, it's tilting to the right. And that really, intrigued me. And when I tilted my theodolite to measure the angle, it appears to be about 1.6 degrees. And that was the clue I was looking for, because there was a wind blowing from the left to the right. And I quickly realized what was happening. I speculated that it had been the evaporative boundary layer. And sure enough, because that wind, it's blowing to the right, the properties are changing across the horizon, you know. Close to the left, light kind of propagates through drier air, but light coming from the horizon on the right propagates more through the moist air, and thus the light propagation path experiences more upward refraction, making the horizon look lower, thus confirming my speculation that it's really this evaporative layer. That's why folks in really humid climates, you know, in the Midwest or the Gulf, where it seems like those clouds are just dropping into the ocean really close, it's not really that the Earth's curvature is doing this. It's really refraction upwards. But out here on the west coast, where the water is cooler and there's more dry air, we can see a lot farther because we don't have this evaporative boundary layer. However, it's still there at times. So on the first of the year, when I took these awesome pictures, I went up on Point Dumay eventually and measured the elevation angle to the horizon, or the depression angle, and it's about 2 degrees. So there's still refraction out here. The wind was blowing from the west, so I imagine there's some moisture. So with that kind of an angle, you'd mean my observational height, should be over 10,000 feet, but it's not. Up here it's about 200 feet. So yeah, it's really this bizarre, evaporative layer refraction that's occurring. Very fascinating, folks. So the conclusion here, for me at least, is the atmosphere is making it appear that there is a curve. It's really interfering with the flat earth phenomena. So from ground level, folks, we will never be able to see very far. Regardless of how good infrared is. The atmosphere poses 2 challenges. One is attenuation. There's haze and we just can't see too far. But then there's refraction. So we beat haze with the infrared and extend the range of visibility, but we still have to contend with refraction. And so that's why I've taken to the skies with my infrared cameras, because once we get above that 2 degree depression angle, that's when the earth really starts to show its true flatness. But if you pick an observational site like I have over here, so you go over water just a little bit and then you observe over land, then you can trick the atmosphere into revealing its secrets. But yes, folks, the earth is quite flat once we understand what refraction is doing to us. I hope this has been an eye-opening presentation for you guys. Thanks for watching.